Every Turing laureate played a key role to advance computing, and our first speaker is going to talk about the impact of their accomplishments, her accomplishments. The 2008 Turing laureate, she is Institute Professor, Massachusetts Institute of Technology, Barbara Liskov.
Thank you, Wendy. And I was asked to give this talk last fall, and I agreed to do it with some trepidation because although it's clear there's been tremendous impact from the work of the Turing laureates, there have been 50 Turing Awards, and there's no way you can talk about all of them. So it was a dilemma. And if I can find the way to advance things. Press the green, what green button? Oh, on here, okay. So I decided to resolve this dilemma by focusing on the first 20 years. I didn't want to play favorites or anything like that. And actually, the first 20 years is a really good thing to focus on because as I talk about who got the awards and what they did, you see the field of computer science coming into focus. I decided also to start by talking about the first 5 winners, and then after that I'll switch and talk about the remaining winners by field, the sort of standard fields of computer science, namely theory, AI, and systems. And I'll spend most of the time talking about systems because that's my area, so I have the most to say, but also because the majority of the winners of the Turing Award have been in systems, both in the first 20 years and also across all 50 years. I want to point out that at the time the Turing Award was created, there was no computer science, and actually there was a kind of a negative attitude about programs and programming across the community of scientists where this work was being done. And I can talk about this personally because I encountered it. There was a kind of an anti-intellectual attitude. There's no intellectual content here for both programming and programs. And so you can imagine that when the Turing Award was created, I wasn't in the room at the time, so I don't know what the founders were thinking, but there was probably an intention to start to develop this as a valid intellectual field, to put a stake in the ground to really establish this as a field. So I can also imagine there was a great deal of trepidation about those first award winners, because when you're in that kind of atmosphere, you want to make sure you make the really good choices so that nobody can say, oh, that person's a lightweight, excuse me, and shouldn't have gotten the award. Of course, we're always careful with the Turing Awards, but I think those first 5 mattered a lot. So the first one went to Alan Perlis in 1966. And Alan was a programming language person, and he developed a language called IT in 1956. You have to understand how early this was. The first stored program computer became operational in 1949, and at that point there was just machine language. So Alan already had a higher level language, not as high level as what we have today, a kind of a Fortran-like thing, relatively machine transportable, relatively machine independent, and as a result it was used at many academic institutions in the early years. Alan was the chair of the United States representatives to the Algol 60 committee, and he contributed to the design of Algol 60, and he was also a spokesman for computer science, arguing that there was very important intellectual content in both programming and programs, and that programming languages were a very important subfield there. In addition, he helped to develop the first computer science curriculum. He was the editor of the communications of the ACM and also the president of ACM. The second award went to Morris Wilkes, there he is, in 1967, and Morris developed the first stored program computer. He was the chair of the group at Cambridge. The machine became operational in May of 1949. It's considered to be the first practical machine because actually it was up and running and ran jobs for the following year. Morris was interested in both hardware and software. He wrote a book on programming. He's credited with understanding the importance of program libraries. He also invented microprogramming as a way of simplifying the job of building hardware. Here are the remaining winners of the first 5 years. Richard Hamming, who got his award for his work on error detecting and correcting codes. Marvin Minsky, I'll talk about Marvin a bit later. And then James Wilkinson in 1970 for his work in numerical analysis. I think what you see here is the defining of the field. So we have hardware and software, we have AI, and then we have code work like Hamming's, which has come to be thought of as kind of just outside the boundaries of computer science. You know, people were not certain what the boundaries were. And the Wilkinson work in numerical analysis is definitely a kind of theoretical computer science. It's just that it's not the main part of what we think of as theoretical computer science. However, I can tell you when I was a student at Stanford, there were no courses in theoretical computer science, but I was required to pass a qualifying exam in numerical analysis. Okay, so now I'm going to move on and talk about the fields, and the first is theory. And the first winner, not surprisingly, was Don Knuth. He got the award in 1974, and Don's the one who helped us understand a kind of a good mathematical, understandable way of analyzing algorithms, and his books had a tremendous amount of impact. Dan was not just a theoretician, he also was very interested in programs, in programming. He built compilers, and of course later on, after he got the award, he invented tech. The second award in theory in 1974 went to Dana Scott and Michael Rabin, and they were honored for a paper they wrote, Finite Automata and Their Decision Problems, in 1959. That was when the paper was written, and the citation said they introduced the notion of non-deterministic automata, which is a very central notion in theoretical computer science. Just as an add-on, I took courses from Dana when I was at Stanford. There was no theoretical computer science, but Dana taught courses in logic, and I took those courses. The next award in theory went to Stephen Cook. I'm sorry he's not here today. He wrote a very important paper called The Complexity of Theory Proving Procedures in 1971. He got the award in 1982, and he's credited with establishing the foundations of NP completeness, another fundamental concept in theoretical computer science. And then the final award in theory went to Dick Karp in 1985. Dick published a paper, Reducibility Among Combinatorial Problems, in 1972, just 1 year after Steve Cook's paper, and he was cited for his contributions to theory of algorithms, especially theory of NP completeness. So what strikes you when you look at these 4 winners is here are the foundations of modern theoretical computer science. So really a very nice, and they're giants in the field, so it was a wonderful set of awards. Okay, now I'm going to move on to AI, and there were 3 awards in AI, and they all happened in the first 10 years. The first went to Marvin Minsky in 1979, then John McCarthy in 1971, and then Herb Simon and Alan Newell in 1975. Rather than talk about their individual contributions, actually you could say that their citations all said the same thing, helped to found the field of AI, define what it meant. They are the founders of the field of AI. What I decided to do was just make a couple of comments about what was happening. The first was that these people had extremely broad interests. They were interested in writing programs to do AI-type things, you know, thinking, learning, planning, looking, you know, robotics, all that sort of stuff. And of course, to build programs like that is a tough job. And you're not going to get very far if you have to do this on a bare machine using machine language. So they were interested in all the infrastructure that was needed to get that off the ground. So programming languages, operating systems, et cetera, et cetera. And I'm going to talk here specifically about John McCarthy. John was my supervisor, so I know his work particularly well. And I would say also he was in some sense the broadest. He was all over the place. So if you look at some of the stuff that John did, well, he invented Lisp, the main AI language. Lisp was not the first one, though. IPL was developed by Newell and Simon, and that was the first one, so John built on that. He invented garbage collection. He was part of the team that developed the notion of time sharing, worked on the CTSS system when he was at MIT. He was very interested in reasoning, both about how programs reason and also about how do we reason about the correctness of code. And he also coined the phrase utility computing, which is particularly interesting today when you think about what's going on with cloud computing. The other thing about these people is that they focused on how people do things. I mean, what else are you going to do? If you want to write a program that acts intelligently, you have to have some model. So they thought about how people did things and then used that as a way of putting their programs together. But there was another side to this story, because as you think about how people do things in a computational way, that's a new way of looking at human psychology. And so they were interested in both sides of that question. And I'm just going to mention here that Marvin Minsky did a lot of work with Seymour Papert on how children learn. So that was one example of what was going on there, the theory of learning for people. In the case of Simon and Newell, it was sometimes a little difficult to tell what they were more interested in. Sometimes it seemed like maybe human psychology came first and programs came second. Okay, now I'm going to move into systems, and of course I've already talked about two people in systems. And I'm going to break this up into some sub-areas of systems. So there were 2 awards in databases. The first went to Charley Bachmann in 1973. Charley developed a system while he was at GE, I believe, called IDS. That stands for Integrated Data Store. That system was actually operational around 1963. So that was the first database system that people started to use. And what it consisted of was a file system where the data was stored, but the programs didn't interact with the files directly. There was a command language that they could use to interact with it, so they were sort of saved from all those details of how files are organized, and also the system kept track of interrelationships among the data in the different files. In 1981, Ted Codd got the award for his work on the relational model. That was published in 1970, and of course, that is the predominant model today. But during the 1970s, there were debates in the database community about which of these 2 models was going to predominate. In the end, after there were some successful implementations of the relational model won out, but there are still remnants of the IDS model in the integrity constraints that are part of the modern database systems. There was an award in operating systems in the first 20 years, and we have Ken Thompson here. Dennis Ritchie and Ken Thompson got their award for the work they did on Unix. Unix became operational in 1970 and is still in widespread use today. I mean, that is really amazing. And I think that speaks to they got the design right. Those of us who do design know it's really hard to get the design right. You have to keep the right stuff, throw out the right stuff. You have to present it to people in a way that makes it usable. And they managed to do that. They took the work in Multics, which got awarded later, and they just managed to make it a little simpler and better so that it was really widely used. Another thing they did, I think not in the very beginning, but a bit later, was they implemented Unix in C. And by implementing it in a higher level language, even though C is not real high level, they made it much more easy for people to transport it. Okay, now I'm going to move on to the final awards, and these were all in the programming languages and methodology field, and I just want to talk about that field a bit. This was an extremely active field in the 50s and 60s and actually into the 70s. And one of the things people were arguing about is, could there even be a, quote, universal it's a higher level programming language that could be used for applications in any domain, no matter what that domain was. And of course, today we know there are such languages because we use them in building our code. One of the reasons people were very concerned about that was because, of course, they were concerned about the performance of their code. And compilers were not very well developed at this time, and so they didn't necessarily produce very good code, so that was a problem. And then in addition, they were very interested in how should programs be designed, how should they be organized, and how can programming languages help. So first I'm going to talk about two of the award winners that you might think of as being sort of pre-ALGOL 60. ALGOL 60 was a real important step forward in the programming language area. And what I mean here is that their work was not particularly influenced by ALGOL 60. It was sort of off separately. First there was John Bacchus, who was the leader of the team that developed Fortran. And then John was a member of the committee that went to the ALGOL 60, the American group in the ALGOL 60 committee, and while he was there, he developed BNF along with Peter Nauer. Ken Iverson got his award in 1979 for his work on APL. APL actually was, the first publication was in 1962. Now, and I just wanted to mention that there were several Turing Award winners on that ALGOL 60 committee. I've talked about Perlis, who was the leader, and Bacchus, but John McCarthy was also on that committee, and he's credited with getting recursion into ALGOL 60 and also conditional expressions. Okay, now I'm going to move on to the post-ALGOL 60 work, and the first of these winners was Dijkstra in 1972. Dijkstra was a champion for getting people to understand that programming was an intellectual challenge. And I think he did this beautifully in his paper on GoTo Considered Harmful, because he simply argued that when you try to understand what a program is doing, you reason from the program text, which is static, but you're thinking about the execution of that program, which is dynamic. And then he went on to say, to make this reasoning as easy as possible, let's try to keep those two close together, and the GoTo got in the way. It was just a very straightforward, easily understood argument, and he won the battle because the GoTo disappeared. Dijkstra was also interested in program design. He wrote many papers about that, and then he got very interested in this notion of correct by construction, where his idea was, you don't even have to debug, you can just reason about the correctness of your program ab novo. He probably went a little too far there. You can't develop a big program purely from reasoning about its correctness, but there's absolutely no doubt that keeping in mind and thinking about the correctness of your program, the specifications, the invariants, and so forth, is a very important way to keep the complexity of your code under control and to find errors that might otherwise be missed. In addition to that other work, there's he did a bunch of other stuff, and I'm just going to mention here the THE operating system, which was very important in the systems area, and he invented the notion of semaphores. The second award went to Bob Floyd in 1978. Bob was amazing. Floyd was absolutely amazing. He worked on compilers, and he introduced the notion of predicate grammars and production systems, which were very important in the early work on compilers. And then he wrote this remarkable paper, Assigning Meaning to Programs in 1967, which was the first paper about providing an axiomatic semantics for programs and programming so that you could reason about their correctness and understand what the statements did. He did this using flowcharts, but he was really talking about what came to be called Hoare triples, where you could say, the way you define statement S is you talk about how a precondition leads to a postcondition when you execute that statement. He also did work on program verification and program synthesis. And then the next award went to Tony Hoare in 1980, and he was cited for design and definition of programming languages. He wrote the amazing paper, Axiomatic Basis for Computer Programming, in 1969, in which he picked up on the work of Floyd and turned it into a way to define the semantics of programming languages. So there's the Hoare triples. And using an axiomatic way of defining the semantics of programming languages is really the way to go, because using axioms like that means that your definition of the semantics is free of any implementation detail. And therefore, the designer of the implementation is perfectly free to do anything that fits that definition without having to worry about extraneous stuff. And then, of course, on the other side of the coin, what's particularly important is you can take that definition and now you can start to reason about whether your program works by using the very same definition. Tony did a bunch of other stuff. A paper I particularly like is his data representation paper, where he showed how to prove the correctness of abstract data types. And then the final winner in this group is Nikolas Dirt in 1984 for his sequence of innovative programming languages, Euler, Algol W, Modula, and especially Pascal, which was a very important academic programming language for many, many years because it was nice and simple and also easily transported. Dirt developed a very nice transportation technique here. He had a second language called P-code, which was an abstract assembly language, and then the compilation process was Pascal to P-code, and then P-code to the machine. First there were interpreters, later there were compilers, and you can see here JVM. And Dirt said that had he understood how important P-code was, he would have spent more time designing it. And that's the end. There's been tremendous impact, just among these first 20 years. And I just want to close by saying I had to do some research to get this talk together. And it was a lot of fun. It was informative, and it was also really enjoyable. You learn about these people and their lives as well as what they did. And you might enjoy doing some of this too, and the place to go is to that URL that I have up there on the screen. That'll get you started. Thank you very much.
She stopped perfectly on time. Thank you so much. Would you join me again? That was an amazing talk. Barbara's going to exit stage right. I was just thinking how many, Barbara's mentioning a lot of the systems I used to teach about in the 1980s as a junior lecturer in Southampton, and I never thought that when I grew up that I'd actually get to meet so many of my heroes who had designed the systems that I was teaching about.